Hello everyone, welcome to this video. In this video, we are going to learn about Hubbard regression using OpenMathAI. So, let's get started. What is Hubbard regression? Hubbard regression is a supervised machine learning algorithm used to predict a continuous numerical value, just like linear regression. However, unlike linear regression, Hubbard regression is designed to handle outliers. Outliers are data points that are very different from the rest of the data and can cause a normal linear regression model to produce inaccurate predictions. Hubbard regression combines the advantages of two error calculation methods. For small prediction errors, it behaves like linear regression by squaring the errors. For very large errors, it switches to using the absolute error instead of the squared error. Because of this, extreme values have much less influence on the final model, making Hubbard regression more robust and reliable when the dataset contains unusual observations. Imagine you want to predict the price of a house based on its size. Most houses follow a normal pattern where larger houses have high prices. However, suppose one big house is listed at an extremely low price because the owner wants to sell quickly. This is an outlier.in. This dataset 5,600 at price is very low compared to the other price, so it's an outlier. We use this dataset for Hubbard model, so let's get started. Open OpenMathAI. In this demonstration, we use the house price prediction using Hubbard regression model. Click Create New Project. Enter the project name as House Price Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There is also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually, or use Smart Suggest for automatic recommendations. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the Hubbard model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Start Multimodal Training. Review the training configuration. Test Data Split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. Modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits a dataset. It is generally derived from metrics such as R-squared, RMSE, and residual errors. Model accuracy. For regression models, accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95, accuracy almost equal to 95%. Click Math and Code Preview. View the generated mathematical equation and source code. OpenMathAI provides expression of the data, detailed explanation of the expression, and an implementation code. Return to the results page and click Deploy Status. Click Export Model. Choose the required export format: ANSI, FMU 2.0, FMU 3.0, Python Bundle, ONNX Hub. Select the destination folder for the exported files. In this demonstration, select FMU 2.0 engine. Click Deploy Engine. In the professional version, OpenMathAI can also generate PowerPoint and PDF reports. Now, Let's see how to use the exported FMU in Twin Simulate. First, open Twin Simulate. Once the software opens, double-click on the workspace to add a new block. In the search box, type FMU and press Enter. Next, click on the FMU block. In the Properties panel, select the File option and browse to the FMU file that was generated by OpenMathAI. After selecting the file, Twin Simulate will load the FMU. Now, you will see a list of input and output variables. Select the required input variables by checking their checkboxes. In the same way, select the required output variable and then click OK. The FMU block will now display all the selected input and output ports. In our example, we have 4 input features and 1 output feature. Next, from a library on the left side, open the Input section and drag a constant block into the workspace. Since we have 4 input features, repeat this step until you have added 4 constant blocks. Now, connect each constant block to its corresponding input on the FMU block. After that, open the Output section, drag a print block into the workspace, and connect it to the output of the FMU block. Now let's provide the input values. Open the first constant block and enter 1200. In the second constant block, enter 5. In the third constant block, enter 7. Finally, in the fourth constant block, enter 180. Once all the values are entered, click Run Simulation. After the simulation completes, the print block displays a predicted output generated by the FMU. This confirms that the exported OpenMathAI engine can be successfully compiled and executed on Twin Simulate.